All right, welcome. So in this video, we're going to move on from the regular languages and start talking about a new set of languages called the context-free languages based around a new model of computation that we're going to look at called the context-free grammar. An example of a context-free grammar that you're probably already familiar with are the rules that govern what makes a well-formed mathematical expression. And a well-formed mathematical expression is one that looks correct and doesn't have any errors in it, and our brains are kind of pattern recognizers that have already conditioned to know what these well-formed equations look like, but we need to actually write code for a computer or a compiler to determine if it's well-formed or not. For instance, in your IDEs, if you write a ill-formed mathematical expression, then you'll probably get a little red underline there somewhere saying this doesn't look right to the IDE or the compiler, and we need, there's some process that scans that to make sure that that is well formed. And how is it doing that? Well, it's using a context-free grammar. So let's just explore this a little bit by looking at the mathematical. Go back to your grade school and imagine you were asked to do something like this. Remember, we've got rules that, again, hopefully our pattern recognizers we've already sort of internalized. We know that multiplications, for instance, come before additions or something, and that brackets have a certain role in telling us what order we should be doing our operations in. So looking at this, again, if we were going to compute some of these operations, which are the ones that we're going to compute first? We need to go to the innermost operations. So we might, for instance, be doing this 3 times 6, and maybe the 12 divided by 3 as our first operations, and computing those out, we might get 18 and 4. After this, the times is still in there, but because of these brackets, that sort of overrules the multiplication part there. So we'll do this addition and this subtraction first. So we're going to end up with a 23 and a 4, and then finally we do the final multiplication to get our answer of 92. Now again, this is something that hopefully we all have internalized and we've been practicing a lot, so we already, we didn't expect anything different from that. But the question then is, how does the compiler know that this is a well-formed mathematical or logical expression when it's, compiling, or how does our IDE do it when it's trying to warn us about potential compiler errors? So again, to make things explicit, on the left-hand side here, I have examples of what might be well-formed mathematical and logical expressions. These are not necessarily in any particular language. These are more mathematical versions of these, for the and the or symbol, for instance. But you can imagine versions of these appearing in your code inside of an if, maybe for some of these logical ones, or as just part of some of your computation for the arithmetic. And again, we know that in our code, there are ways that we can combine the arithmetic into logical expressions as well. Certainly we have experience doing that, and again, our compiler, our program that parses that, needs to be able to understand what that means, because we understand what it means when we write it down, right? Now on the right, I have what we might call ill-formed mathematical and logical expressions. These don't make sense to us. Our internal pattern recognizers should look at them and be like, that doesn't make sense. And the same thing with our compilers and our IDEs. If we wrote something like this in our IDE alone, it would probably get red underlined saying something's wrong here. So this task of finding what is a well-formed or an ill-formed expression is actually, it's a core task of compilers and IDEs, but it is also a tricky one. It's not exactly easy to do. So let's restrict ourselves a little bit to a subset, so that we're not working with the practical real world problem of dealing with all the possible operators that we're using inside say Java or C or Python. Instead, let's just again make a toy example that's easy for us to work with, that we might be able to expand and generalize on later. So let's imagine we're just dealing with numbers, and we're just trying to do addition, multiplication, and parentheses. Okay, so now let's make a more formal definition then of what a well-formed mathematical expression would look like. To do that, I'm going to make a recursive definition, and that's going to be characteristic of our context-free grammars. They tend to have a recursive element to them. So an expression E is going to be well-formed if E is one of these things. The first thing in our list is just a string of digits or bits, i.e. a number. So a number by itself, 42, is a well-formed mathematical expression. Okay, B, if you have another well-formed mathematical expression, E1, and you put brackets around it, that's also a well-formed mathematical expression. So for instance, 42 with brackets around it is a well-formed mathematical expression. It's a bit redundant, but it is one, okay? Next is if you have two well-formed mathematical expressions, E1 and E2, and you put them together in a sum, you get a well-formed mathematical expression. We can start to see how putting these definitions together, we can get all kinds of things. Now with addition, now we could have 2 plus 3 inside brackets plus 4 and or whatever else, you know, we with these ones. And now we go to the next level, D here. We can do the same thing with multiplication. You have two well-formed mathematical expressions that are E1 and E2, and now you can multiply those together. So again, we can put them in brackets, multiply them together, put that in brackets, add it to something, put that in brackets, multiply it to something else. As long as you keep recursively doing this, and the thing that you have at the core are just more well-formed mathematical expressions. At the very bottom, they're all just going to be strings of numbers, potentially added or multiplied or placed in brackets in some kind of long string of symbols. That's exactly what we write when we write down, you know, arithmetic sequences, and we would want our compilers to be able to interpret that in the same way that our minds do. So what we've actually described there in that definition is a context-free grammar, and we tend to not make it in that full definition-y way that we just did there. Instead, we like to use this sort of notation where we define the grammar. And here, again, the recursive structure is pretty clear. We're actually using two what are going to be called rules or variables for this grammar, E and N here. And maybe let's just start with the N one here. N, I have a very simple example here. N can be replaced with two copies of itself, but eventually all the n's have to be replaced by one of these numerals. Notice these don't appear on the left-hand side of any rules. 0 isn't on the left-hand side, 4 isn't on the left-hand side. What that means is these are terminals, or these are not rules, these are symbols probably in the language that we're looking at. So in this case, we've got lots of symbols, 0 up to 9. Other symbols that are not in, or symbols from the alphabet would be the plus symbol here, the multiply symbol here, and the brackets, because again, they are not variables. They don't appear on the left-hand side here, okay? But this n variable, we can basically see that we can make any string a number we want by starting out by saying we want 5 strings, maybe we want, or 5 numbers, 5 numerals, I should say, in our number. Let's say we want the string 1, 2, 3, 4, 5. Then we would just follow this rule a number of times until we have 5 copies of n, and then we would just replace the first one with a 1, the second with a 2, 3, 4, and 5, and we would get the string that we want. Now, the rule E here has to do with more of that nesting these numbers inside some arithmetic equation by either adding them together, multiplying them together, or putting them in brackets as needed. But eventually, you'll notice this is recursive. The only way to terminate this infinite recursion, because it's E goes to E, E goes to E, E goes to E, is those E's eventually have to go to N's. And those N's, again, we can follow the recursion all we want, but eventually those N's have to terminate with numbers. So at the end, if we have eliminated all copies of E and all copies of N, we will have generated a string that should be a well-formed arithmetic sequence. So here I've got just another example. Since we've been working with the binary alphabet primarily so far, not the decimal alphabet there, we might consider binary arithmetic here. Now again, I call it the binary alphabet, but that's only for the numbers. We still have pluses, multiplies, and brackets in this particular grammar's alphabet, but the numbers that we would produce would only be binary numbers in this case. There is one sort of peculiarity about this grammar that we might want to change, and that is that this grammar permits leading zeros. So there's nothing in this grammar that does not say, hey, we could, if we want, follow this and n as many times as we want, and then select zeros for all of them. So we can just have 0, 0, 0, 0, 0, 0, 0, 0, big long 0. Usually we get rid of leading zeros in most of our numbers, but this grammar does not account for that. We could change the grammar to say that it has all numbers must start with a non-zero unless it's just 0 by itself. But you know, that would have been a more complicated example, and I didn't want to go down that particular path. All right, now let's take a look at a particular language of interest. Remember this one from some of our earlier videos. This is our first language that we showed was not regular. And we might ask ourselves, is it possible to show that it is context-free? Or another way of saying that, is it possible for us to make a grammar for this? We could not, for instance, make a regular expression for this, but we might be able to make a context-free grammar. This grammar is actually one of the simpler grammars that you can make, and it uses a technique that's kind of important in a lot of the grammars that we might use. It kind of was being used in our previous example, although not exactly. This particular grammar allows us to grow our string on the left and on the right. So in some sense, when we're generating it, we're growing it out from the middle. And that's going to be important if, at least in this case, we want to match up the number of zeros we're growing on the left with the number of ones on the right. Every time we follow this rule, we're going to get one copy of a 0 and one copy of a 1. And they're going to spread out as we do it. Follow that how many times you want, say n times, and you will have n copies of zeros, n copies of 1. And when you're done, finish it off by just getting rid of that last s in there with an epsilon, and you'll get equal numbers of ones and zeros. Now, think about this yourself. In our non-regular languages proofs, we considered a couple variants of this language. What if the number of ones should be more than the number of zeros, or less than the number of zeros? Or what if they should just always be not equal to each other in some way? Okay, how can we ensure that? All right, these are questions that pose yourself and maybe do as a quick little exercise. How can we change this grammar into some of those other variants? But for our case, let's go ahead and come up with some of the definitions that are attached to the grammars now. One thing that we haven't really mentioned is the sequence. When we're following the grammar and we're replacing rules, what we're doing is we could say we're generating a string. In some cases we are. Or we could also say we're deriving the string. We're trying to figure out the path in the grammar that leads to the string that we're particularly looking for. Okay, so well, let's just formalize that here in this definition that says a derivation then of some particular string is going to be a sequence of substitutions within that grammar G that yields that string W, the string that we're looking for. This is also technically a definition of what it means to yield a string. So let's explore this a little bit. So this is a grammar that we're working with. Again, a very simple example. We can see straight up that S derives the string epsilon. Okay, and it does that in one step. We can just replace the S with epsilon and we're done. That's easy. So the derivation here is a one-step derivation. You'll notice that in our rules we use this sort of single arrow to depict what rules you can follow, but when we're doing derivations we use this sort of double barred arrow to distinguish between the two of them. Let's look at a slightly more complicated string then. That would be the string 0011. We can see that we would follow the first rule once, which would end up with a 0 and a 1. Then we would follow it again. Notice that the first 0 and first 1 kind of get pushed to the outside as that inner S gets replaced by this new 0 S1. And then finally that inner S gets replaced with an epsilon to give us our final string. And again, this would be our derivation. Let's look at our binary arithmetic example. This one's a little bit longer. In this case, we have, I want, 2 plus 3 times 2, it looks like, if this is binary. And let's see how we can derive that with our more complicated grammar. So let's start out, we always start with our start variable. In this case, it's E. It's usually the first one if it's not stated explicitly. Sometimes we make the start variable S. That's why we picked S in that last example. But in this case, we were using this for, equation or something like that. So we got E here as our start variable. Using that, what are we going to replace? Well, we kind of need to look at the pattern here and think, well, what are we going to replace? This is also how the compiler determines what order it should be doing its operations in by following a grammar that helps it know what order it should apply. In this particular pattern that we're looking at here, it looks like the plus here is the first one, which would mean when we were calculating the value of this expression, it would be the last one that we would operate on. It would be the first one in our derivation, but it would be the last one that we carry out in our order of operation. So once we see that, we're going to end up with an expression on the left and an expression on the right. Sure enough, we've got those. That's what we're looking for up here. So we actually have a choice of which E we want to replace here. And normally, if we were doing this, we would only do one at a time, but because I wanted to save a little bit of space on my slide, I'm going to be replacing them both. Normally, if we do it one at a time, we sometimes pick the leftmost one first. We would call that a leftmost derivation. We could pick the rightmost one too, and we call that a rightmost derivation. We typically do leftmost just because that's the order we read in, at least in English. And so, again, I'm going to do the replacement here. So the first E, it looks like I'm going to replace with an N, because I'm trying to make this number here. But the second E, after the plus, I got a whole bunch of stuff going on here. I need some brackets, so that one got some brackets added to it. In my next step, same thing, I'm going to try and do, double up on my replacements here. So I'm going to replace my N here. I'm trying to make this number. I can't just pick one because then I won't have another N for the 0, so I need to do this double up N first. And then inside my E here, again, I've got a lot going on here. I'm trying to make this whole pattern here, so now I need to multiply. So I've replaced that E with E times E. Moving to the next step, well, both of those ends, I'm going to replace with the numbers I need, 1, 0, 1, 0, okay. My E is in there, no more multiplies or brackets or whatever, we just got numbers going on here, so I'm going to replace those E's with N's so I can start making my numbers. Again, both those numbers have 2 bits in them, so I'm going to have to expand them. And then in my last step, I'm going to replace them. Now again, notice if I wasn't doubling up and in some cases tripling or quadrupling up in my replacements here, we would have ended up with a really long derivation here. That's okay, that's how derivations look, but it's going to help us, again, by going backwards, know what order of operations we should be carrying out. Okay, another way we can represent derivations is what we call a parse tree. And so this is just a simple example of that. Parse trees are more visual and can help us see the pattern a little bit easier, although for longer strings and for larger grammars they can be very big and therefore sort of unwieldy and hard to draw. So I've hinted at this already, but a context-free grammar is a generator of strings, not a detector of strings. And we saw this in a contrast in our regular languages. We first started looking at automatas, DFAs and NFAs, and they would take a string as input and just tell you yes or no, this is in the language, whereas regular expressions have this pattern that you can use to generate or maybe match to strings to determine if they're in the language, or generate all the strings in the language, or generate a string in the language. These two different kinds of models of computation, they just sort of have different ways of working, detectors and generators, and context-free grammars just happen to be another kind of generator. And you might ask, well, is there a related detector? Yes, there is, and we're going to talk about that in a future video. It's called a push-down automata. But our context-free grammar is then just going to be one of the generators. So one way we think of context-free generators or context-free grammars as generators is that they generate all the strings. And they do that by following all the paths possible in their rule set. All right, I think we're ready now for a formal definition of grammar, of a context-free grammar. Just like we've seen for regular expressions or deterministic and non-deterministic finite automata, a context-free grammar is going to be a 4-tuple. Okay, and remember our other ones were 5 tuples and so on. This is going to be a 4-tuple. It's going to have 4 parts: V, sigma, R, and S. Sigma is already we've been using sigma as our alphabet over the language, and that's also going to be the same in our context-free grammars. Here, though, we're going to say that they're the set of terminals. We've just given them a slightly different name. Those are the symbols in the alphabet that are not variables, that do not need to be replaced with anything else. Once they appear in the string, they don't get replaced. So that's what the sigma is. And in that discussion there, I also kind of said what V is. V is the set of the variables. Those are they're not elements of sigma. They're not part of the language, as we can see here, that these two sets have to be disjoint from each other. They can't have any overlapping symbols. And that's because all the variables need to be replaced in generating any string. And once you've replaced all the variables, all you will be left with are sets of terminals, and therefore you'll have a string over the alphabet. Now R is the set of rules. Now each rule is going to be a mapping. On the left-hand side, there's going to be some variable. But on the right-hand side, there's going to be a string of variables and potentially terminals that you can replace that variable with. And as we saw in some of our examples, that sometimes we're replacing a variable with another variable or string of variables, but sometimes it's a mix of a string of variables and terminals, or just terminals by themselves. Finally, we need to pick one of the variables out of our set as our start variable, and that's just like highlighting one of our states in one of our state diagrams as our start state. We need to know where to begin the process. And in tradition, we call that one S for start. Of course, that convention can be overruled if you want. So one of the verbs we were using in one of our earlier definitions was the verb to yield. How do we yield something? And that's basically just explaining in, again, formal terms how a rule replacement works. Okay, so let's just formalize that as much as we need to here. So let's say we have U, V, and W, and these are all strings of variables and terminals. They could have variables in them or terminals. Think of that however you like, okay? And we've got this rule here. A is the variable of the rule, and W is some other string of variables and terminals, as we already said. Okay, so A is saying you can replace the rule A with W. Then what we will say is we'll say that this string here, UAV, remember U could have variables and terminals in it, same with V, this big long string, whatever it might be, yields the string UWV. All we've done here is replace the A with W following this rule. And then we would write this using the double bar as we've been doing in our previous definition, in our previous explorations of derivations. So we've kind of already used this definition in some of our examples, so we kind of seen it in action, but this is just us adding some formal draping to it so that now we can say use it in a proof, not just in some examples. And continuing that, now we can talk about what it means to derive a string in more formal terms. And we can do that here. Again, we're defining the term derives, but also this symbol with the star over it. We're still using the yield symbol, but the star over it means basically you can follow it as many times as you want. So it's not just one step of the rule that gets you from U to V. It's as many steps of rule replacements as you need to get from U to V. And again, that's just formally spelling this out. It's saying that U derives V either if they're the same, so any string derives itself, or if you can get the sequence of intermediate strings where you say, okay, U gets to U1, which gets to U2, eventually deriving to V. And if you get that for some finite sequence, then you derive a particular string. Now, taking all that formal machinery together, the reason we're setting it up is so we can make a definition like this that says, okay, well, now that I have a grammar G, what is the language of that grammar? Well, we would say, well, it's all the strings over the terminals that can be derived from that grammar, which again, implicitly is already what we might expect that to be. So again, adding formal drapery to maybe what our intuition is about these relationships. All right, so this has been an introduction to context-free grammars. I hope you enjoyed this video, and we'll see you in the next one.